So hello everyone and welcome to NEETOPEDIA. Today we'll be starting with chemistry audiobooks and kicking it off with hydrogen. So let's get started. Unit 9, Hydrogen. Hydrogen, the most abundant element in the universe and third most abundant on the surface of the globe, is being visualized as the major future source of energy. Hydrogen has the simplest atomic structure among all the elements around us in nature. In atomic form, it consists of only one proton and one electron. However, in elemental form, it exists as diatomic molecule and is called dihydrogen. It forms more compounds than any other element. Do you know that the global concern related to energy can be overcome to a great extent by the use of hydrogen as a source of energy? In fact, hydrogen is of great industrial importance, as you will learn in this unit. 9.1 Position of hydrogen in the periodic table. Hydrogen is the first element in the periodic table. However, its placement in the periodic table has been a subject of discussion in the past. As you know by now that elements in the periodic table are arranged according to their electronic configurations. Hydrogen has electronic configuration 1s1. On one hand, its electronic configuration is similar to the outer electronic configuration of alkali metals, which belong to the first group of periodic table. On the other hand, like halogens, it's short by one electron to the corresponding noble gas configuration, that is helium. Hydrogen therefore has resemblance to alkali metals, which lose one electron to form unipositive ions, as well as with halogens, which gain one electron to form uninegative ion. Like alkali metals, hydrogen forms oxides, halides and sulfides. However, unlike alkali metals, it has a very high ionization enthalpy and does not possess metallic characteristics under normal conditions. In fact, in terms of ionization enthalpy, hydrogen resembles more with halogens. Ionization enthalpy of lithium is 520 kJ per mole, fluorine is 1680 kJ per mole, and that of hydrogen is 1312 kJ per mole. Like halogens, it forms a diatomic molecule, combines with elements to form hydrides and a large number of covalent compounds. However, in terms of reactivity, it is very low as compared to halogens. In spite of the fact that hydrogen to a certain extent resembles both alkali metals and halogens, it differs from them as well. Now, the pertinent question arises as where should it be placed in the periodic table? Loss of electron from hydrogen atom results in nucleus H+ of 1.5 into 10 to the 3 picometer size. This is extremely small as compared to normal atomic and ionic rate sizes of 50 to 200 picometer. As a consequence, H+ does not exist freely and is always associated with other atoms or molecules. Thus, it is unique in behavior and is therefore placed separately in the periodic table. 9.2 Dihydrogen. 9.2.1 Occurrence. Hydrogen is the most abundant element in the universe, principal element in the solar atmosphere. The giant planets Jupiter and Saturn consist mostly of hydrogen. However, due to its light nature, it is much less abundant in Earth's atmosphere. Of course, in the combined form, it constitutes 15.4% of the Earth's crust and the oceans. In combined form, besides in water, it occurs in plant and animal tissues, carbohydrates, proteins, hydrides, including hydrocarbons and many other compounds. 9.2.2 Isotopes of hydrogen. Hydrogen has three isotopes: protium, deuterium and tritium. Can you guess how these isotopes differ from each other? These isotopes differ from one another in respect of the presence of neutrons. Ordinary hydrogen, protium has no neutrons, deuterium has one and tritium has two neutrons in the nucleus. In the year 1934, an American scientist, Harold C. Urey, got Nobel Prize for separating hydrogen isotope of mass number 2 by physical methods. The predominant form is protium. Terrestrial hydrogen contains 0.0156% of deuterium, mostly in the form of Hd. That will do 12.33 years. Since the isotopes have same electronic configuration, they have almost the same chemical properties. The only difference in their rates of reaction is mainly due to their different enthalpy of bond dissociation. However, in physical properties, these isotopes differ considerably due to their large mass differences. 9.3 Preparation of dihydrogen. There are a number of methods for preparing dihydrogen from metals and metal hydrides. 9.3.1 Laboratory preparation of dihydrogen. Number 1. It is usually prepared by the reaction of granulated zinc with dilute hydrochloric acid. That is, zinc plus 2H plus gives Zn2 plus H2. Number 2. It can also be prepared by the reaction of zinc with aqueous alkali. Zinc plus twice NaOH gives sodium zincate plus H2. 9.3.2 Commercial production of dihydrogen. The commonly used processes are outlined below. Number 1. Electrolysis of acidified water using platinum electrodes gives hydrogen. That is, twice H2O on electrolysis gives 2H2 plus O2. Number 2. High purity dihydrogen is obtained by electrolyzing warm aqueous barium hydroxide solution between nickel electrodes. Number 3. It is obtained as byproduct in the manufacture of sodium hydroxide and chlorine by the electrolysis of brine solution. During electrolysis, the reaction that takes place are: at anode, 2Cl- breaks to form Cl2 plus 2 electrons. At cathode, 2H2O plus 2 electrons gives H2 plus 2OH minus. The overall reaction is 2Na plus 2Cl- plus 2H2O gives Cl2 plus H2 plus 2Na plus 2OH minus. Number 4. Reaction of steam on hydrocarbons or coke at high temperatures in the presence of catalyst yields hydrogen. That is, CH4 plus H2O at 1270 Kelvin and nickel as catalyst gives CO plus 3H2. The mixture of CO and H2 is called water gas. As this mixture of CO and H2 is used for the synthesis of methanol and a number of hydrocarbons, it is also called synthesis gas or syngas. Nowadays, syngas is produced from sewage, sawdust, scrap wood, newspapers, etc. The process of producing syngas from coal is called coal gasification. Carbon plus water at 1270 Kelvin gives carbon monoxide plus hydrogen. The production of dihydrogen can be increased by reacting carbon monoxide of syngas mixtures with steam in the presence of iron chromate as catalyst. Now, carbon monoxide plus water at 670 Kelvin and catalyst gives carbon dioxide plus hydrogen. This is called water gas shift reaction. Carbon dioxide is removed by scrubbing with sodium arsenite solution. Presently, 77% of the industrial dihydrogen is produced from petrochemicals, 18% from coal, 4% from electrolysis of aqueous solution, and 1% from other sources. 9.4 Properties of dihydrogen. 9.4.1 Physical properties. Dihydrogen is a colorless, odorless, tasteless, combustible gas. It is lighter than air and insoluble in water. Its other physical properties along with those of deuterium are given in table 9.1. 9.4.2 Chemical properties. The chemical behavior of dihydrogen is determined to a large extent by bond dissociation enthalpy. The HH bond dissociation enthalpy is the highest for a single bond between two atoms of any element. What inferences would you draw from this fact? It is because of this factor that the dissociation of dihydrogen into its atom is only 0.0 due to the high HH bond enthalpy. Thus, the atomic hydrogen is produced at a high temperature in an electric arc or under ultraviolet radiations. Since its orbital is incomplete with 1s1 electronic configuration, it does combine with almost all the elements. It accomplishes reactions by loss of the only electron to give H plus and gain of an electron to form H minus and sharing of electrons to form a single covalent bond. The chemistry of dihydrogen can be illustrated by the following reactions. Reaction with halogens. It reacts with halogens to give hydrogen halides. While the reaction with fluorine occurs even in the dark, with iodine it requires a catalyst. Reaction with dioxygen. It reacts with dioxygen to form water. The reaction is highly exothermic. Reaction with dinitrogen. With dinitrogen it forms ammonia. This is the method for the manufacture of ammonia by the Haber's process. Reaction with metals. With many metals, it combines at a high temperature to yield a corresponding hydrides. Reaction with metal ions and metal oxides. It reduces some metal ions in aqueous solution and oxides of metals into corresponding metals. Reaction with organic compounds. It reacts with many organic compounds in the presence of catalyst to form useful hydrogenated products of commercial importance. For example, number 1, hydrogenation of vegetable oils using nickel as a catalyst gives edible fats, that is, margarine and vanaspati ghee. Number 2, hydroformylation of olefins yields aldehydes, which further undergo reduction to give alcohols. Problem 9.1. Comment on the reactions of hydrogen with chlorine, sodium and copper-2 oxide. Solution. Number 1. Dihydrogen reduces chlorine to chloride ion and itself gets oxidized to H plus ion by chlorine to form hydrogen chloride. An electron pair is shared between H and Cl, leading to the formation of a covalent molecule. Number 2. Dihydrogen is reduced by sodium to form NaH. An electron is transferred from Na to H, leading to the formation of an ionic compound Na plus H minus. Number 3. Dihydrogen reduces copper-2 oxide to copper in zero oxidation state and itself gets oxidized to H2O, which is a covalent molecule. 9.4.3 Uses of dihydrogen. The largest single use of dihydrogen is in the synthesis of ammonia, which is used in the manufacture of nitric acid and nitrogenous fertilizers. Dinitrogen is used in the manufacture of vanaspati fat by the hydrogenation of polyunsaturated vegetable oils like soybean, cotton seeds, etc. It is used in the manufacture of bulk organic chemicals, particularly methanol. It is widely used for manufacture of metal hydrides. It is used for the preparation of hydrogen chloride, a highly useful chemical. In metallurgical processes, it is used to reduce heavy metal oxides to metals. Atomic hydrogen and oxyhydrogen torches find use for cutting and welding purposes. Atomic hydrogen atoms are allowed to recombine on the surface to be welded to generate the temperature of 4000 Kelvin. It is used as rocket fuel in space research. Dihydrogen is used in fuel cells for generating electrical energy. It has many advantages over the conventional fossil fuels and electric power. It does not produce any pollution and releases greater energy per unit mass of fuel in the comparison to gasoline or other fuels. 9.5 Hydrides. Dihydrogen under certain reaction conditions combines with almost all elements except noble gases to form binary compounds called hydrides. If E is the symbol of an element, then hydride can be expressed as EHX or EMHN. These hydrides are classified into 3 categories. Number 1, ionic or saline or salt-like hydrides. Number 2, covalent or molecular hydrides. Number 3, metallic or non-stoichiometric hydrides. 9.5.1 Ionic or saline hydrides. These are stoichiometric hydrides of dihydrogen formed with most of the S block elements, which are highly electropositive in character. However, significant covalent character is found in the lighter metal hydrides such as LiH, BeH2 and MgH2. In fact, BeH2 and MgH2 are polymeric in nature. The ionic hydrides are crystalline, non-volatile and non-conducting in solid state. However, their melts conduct electricity and on electrolysis liberate dihydrogen gas at anode, which confirms the existence of H- ion. Saline hydrides react violently with water, producing dihydrogen gas. Lithium hydride is rather unreactive at moderate temperatures with O2 or Cl2. It is therefore used in the synthesis of other useful hydrides. 9.5.2 Covalent or molecular hydride. Dihydrogen forms molecular compounds with most of the p block elements. Most familiar examples are CH4, NH3, H2O, and HF. For convenience, hydrogen compounds of nonmetals have also been considered as hydrides. Being covalent, they are volatile compounds. Molecular hydrides are further classified according to the relative number of electrons and bonds in the Lewis structure into electron deficient, electron precise, and electron rich hydrides. An electron deficient hydride, as the name suggests, has too few electrons for writing its conventional Lewis structure. Diborane is an example. In fact, all elements of group 13 will form electron deficient compounds. What do you expect from their behavior? They act as Lewis acid, that is, electron acceptors. Electron precise compounds have the required number of electrons to write their conventional Lewis structure. All the elements of group 14 form such compounds, which are tetrahedral in geometry. Electron-rich hydrides have excess electrons which are present as lone pairs compounds. What do you expect from their behavior of such compounds? They will behave as Lewis bases, that is, electron donors. The presence of lone pair on highly electronegative atoms like nitrogen, oxygen, and fluorine in hydrides results in hydrogen bond formation between the molecules. This leads to the association of molecules. Problem 9.2. Would you expect the hydrides of nitrogen, oxygen, and fluorine to have lower boiling points than the hydrides of the subsequent group members? Give reasons. Solution. On the basis of molecular masses of NH3, H2O, and HF, their boiling points are expected to be lower than those of the subsequent group member hydrides. However, due to higher electronegativity of nitrogen, oxygen, and fluorine, the magnitude of hydrogen bonding in their hydrides will be quite appreciable. Hence, the boiling points ammonia, water, and HF will be higher than the hydrides of the subsequent group members. 9.5.3 Metallic or non-stoichiometric or interstitial hydrides. These are formed by many D block and F block elements. However, the metals of group 7 and 8 and 9 do not form hydride. Even from group 6, only chromium forms chromium hydride. These hydrides conduct heat and electricity, though not as efficiently as their parent metals do. Unlike saline hydrides, they are almost always non-stoichiometric, being deficient in hydrogen. For example, LaH 2.87, YbH 2.55, TiH 1.5 to 1.8, etc. In such hydrides, the law of constant composition does not hold good. Earlier, it was thought that in these hydrides, hydrogen occupies interstitials in the metal lattice, producing distortion without any change in its type. Consequently, they were termed as interstitial hydrides. However, recent studies have shown that except for hydrides of nickel, palladium, cerium, and actinium, other hydrides of this class have lattice different from that of the parent metal. The property of absorption of hydrogen or transition metal is widely used in catalytic reduction, hydrogenation reactions for preparation of large number of compounds. Some of the metals, example palladium and platinum, can accommodate a very large volume of hydrogen and therefore can be used as its storage media. 5. Solution. Although phosphorus exhibits +3 and +5 oxidation states, it cannot form pH5. Besides some other considerations, high enthalpy of atomization value of dihydrogen and high enthalpy of value of hydrogen do not favor to exhibit the highest oxidation state of phosphorus and consequently the formation of pH5. 9.6 Water. A major part of all living organisms is made up of water. Human body has about 65% and some plants have as much as 95% water. It is a crucial compound for the survival of all life forms. It is a solvent of great importance. The distribution of water over the Earth's surface is not uniform. The estimated world water supply is given in table 9.2. 9.6.1 Physical properties of water. It is a colorless and tasteless liquid. Its physical properties are given in table 9.3 along with physical properties of heavy water. The unusual properties of water in condensed state are due to presence of extensive hydrogen bonding between water molecules. This leads to high freezing point, high boiling point, high heat of vaporization and high heat of fusion in comparison to H2S and H2SE. In comparison to other liquids, water has a higher specific heat, thermal conductivity, surface tension, dipole moment and dielectric constant, etc. These properties allow water to play a key role in the biosphere. The high heat of vaporization and heat capacity are responsible for moderation of the climate and the body temperature of living beings. It is an excellent solvent for transportation of ions and molecules required for plant and animal metabolism. Due to hydrogen bonding with polar molecules, even covalent compounds like alcohol and carbohydrates dissolve in water. 9.6.2 Structure of water. In the gas phase, water is a bent molecule with a bond angle of 104.5 degree and OH bond length of 95.7 picometer as shown in figure 9.1. It is a highly polar molecule. Its orbital overlap picture is shown in figure 9.1. In the liquid phase, water molecules are associated together by hydrogen bonds. The crystalline form of water is ice. At atmospheric pressure, ice crystallizes in hexagonal form, but at very low temperature, it condenses to cubic form. Density of ice is less than that of water. Therefore, an ice cube floats on water. In winter season, ice formed on the surface of lake provides a thermal insulation which ensures the survival of aquatic life. This fact is of great ecological significance. 9.6.3 Structure of ice. Ice has a highly ordered three-dimensional hydrogen bonded structure as shown in figure 9.2. Examination of ice crystals with X-rays shows that each oxygen atom is surrounded tetrahedrally by 4 other oxygen atoms at a distance of 276 picometer. Hydrogen bonding gives ice a rather open type structure with wide holes. These holes can hold some other molecules of appropriate size interstitially. 9.6.4 Chemical properties of water. Water reacts with large number of substances. Some of the important reactions are given below. Number 1. Amphoteric nature. It has the ability to act as an acid as well as a base. It behaves as an amphoteric substance. In the Bronsted sense, it acts as an acid with ammonia and as a base with hydrogen sulfide. The protolysis of water takes place as follows. H2O plus H2O gives H3O plus OH minus. Number 2. Redox reactions involving water. Water can be easily reduced to dihydrogen by highly electropositive metals. 2H2O plus 2Na gives 2NaOH plus H2. Thus, it is a great source of dihydrogen. Water is oxidized to oxygen during photosynthesis. With fluorine also, it is oxidized to oxygen. Number 3. Hydrolysis reaction. Due to high dielectric constant, it has a very strong hydrating tendency. It dissolves many ionic compounds. However, certain covalent and some ionic compounds are hydrolyzed in water. Number 4. Hydrates formation. From aqueous solution, many salts can be crystallized as hydrated salts. Such an association of water is of different types. Number 1. Coordinated water. Example, CrH2O holds 6, 3 plus, 3Cl minus. Number 2. Interstitial water. BaCl2.2H2O. Number 3. Hydrogen bonded water. In CuSO4.5H2O. Problem 9.4. How many hydrogen bonded water molecules are associated in CuSO4.5H2O? Solution. only one water molecule which is outside the coordination sphere is hydrogen bonded. The other 4 molecules of water are coordinated. 9.6.5 Hard and soft water. Rainwater is almost pure. Being a good solvent, when it flows on the surface of the earth, it dissolves many salts. Presence of calcium and magnesium salts in the form of hydrogen carbonate, chloride and sulfate in water makes water hard. Hard water does not give lather with soap. Water free from soluble salts of calcium and magnesium called soft water. It gives lather with soap easily. Hard water forms scum or precipitate with soap. Soap containing sodium stearate reacts with hard water to precipitate out calcium or magnesium stearate. It is therefore unsuitable for laundry. It is harmful for boilers as well because of deposition of salt in the form of scale. This reduces the efficiency of the boiler. The hardness of water is of 2 types: temporary hardness and permanent hardness. 9.6.6 Temporary hardness. Temporary hardness is due to presence of calcium and magnesium hydrogen carbonates. It can be removed by number 1. Boiling. During boiling, the soluble magnesium bicarbonate is converted into soluble magnesium hydroxide and calcium bicarbonate is changed into insoluble calcium carbonate. It is because of high solubility product of magnesium hydroxide as compared to that of magnesium carbonate that magnesium hydroxide is precipitated. These precipitates can be removed by filtration. Filtrate thus obtained will be soft water. Number 2. Clark's method. In this method, calculated amount of lime is added to hard water. It precipitates out calcium carbonate and magnesium hydroxides which can be filtered off. 9.6.7 Permanent hardness. It is due to the presence of soluble salts of magnesium and calcium in the form of chlorides and sulfates in water. Permanent hardness is not removed by boiling. It can be removed by the following methods. Number 1. Treatment with washing soda, that is sodium carbonate. Washing soda reacts with soluble calcium and magnesium chlorides and sulfates in hard water to form insoluble carbonates. Number 2. Calgon's method. Sodium hexametaphosphate, that is Na6P6O18, commercially called calgon, when added to hard water, the following reactions take place. The complex anion keeps magnesium ion and calcium ion in the solution. Number 3. Ion exchange method. This method is also called zeolite or permuted process. Hydrated sodium aluminium silicate is zeolite or permuted. For the sake of simplicity, sodium aluminium silicate NaAlSiO4 can be written as NaZ. When this is added in hard water, exchange reactions take place. Permuted or zeolite is said to be exhausted when all the sodium in it is used up. It is regenerated for further use by treating with aqueous sodium chloride solution. Number 4. Synthetic resins method. Nowadays, hard water is softened by using synthetic cation exchangers. This method is more efficient than zeolite process. Cation exchange resins contain large organic molecule with SO3H group and are water insoluble. Ion exchange resin is changed to RNA by treating it with NaCl. The resin exchanges Na plus ions with calcium and magnesium ions present in hard water to make water soft, where R is the resin ion. The resin ion can be regenerated by adding aqueous NaCl solution. Pure demineralized water free from all soluble mineral salts is obtained by passing water successively through a cation exchange and an anion exchange resins. In this cation exchange process, H plus exchanges for Na plus, Ca2 plus, Mg plus and other cations present in the water. This process results in proton release and thus makes the water acidic. In the anion exchange process, OH minus ions for anions like Cl minus, bicarbonate ion, sulfate ion, etc. present in water. OH minus ions, thus liberated, neutralize the H plus ions set free in the cation exchange. The exhausted cation and anion exchange resin beds are regenerated by treatment with dilute acid and alkali solutions respectively. 9.7 Hydrogen peroxide. Hydrogen peroxide is an important chemical used in pollution control treatment of domestic and industrial effluents. 9.7.1 Preparation. It can be prepared by the following methods. Number 1. Acidifying barium peroxide and removing excess water by evaporation under reduced pressure gives hydrogen peroxide. That is, BaO2.8H2O plus H2SO4 gives BaSO4 plus H2O2 plus 8H2O. Number 2. Peroxodisulfate obtained by electrolytic oxidation of acidified sulfate solutions at high current density on hydrolysis yields hydrogen peroxide. This method is now used for the laboratory preparation of D2O2. Number 3. Industrially, it is prepared by the auto-oxidation of 2-alkyl anthraquinols. 2-ethyl anthraquinol in the presence of oxygen gives H2O2 plus oxidized product. In this case, 1% H2O2 is formed. It is extracted by water and concentrated to 30% by distillation under reduced pressure. It can be further concentrated to 85% by careful distillation under low pressure. The remaining water can be frozen out to obtain pure H2O2. 9.7.2 Physical properties. In pure state, H2O2 is almost colorless, very pale blue liquid. Its important physical properties are given in table 9.4. H2O2 is miscible with water in all proportions and forms a hydrate H2O2.H2O. A 30% solution of H2O2 is marketed as 100 volume hydrogen peroxide. It means that 1 milliliter of 30% H2O2 solution will give 100 milliliter of oxygen at STP. Commercially, marketed sample is 10 volume, which means that the sample contains 3% H2O2. Problem 9.5. Calculate the strength of 10 volume solution of hydrogen peroxide. 10 volume solution of H2O2 means that 1 liter of this H2O2 solution will give 10 liter of oxygen at STP. On the basis of our equation, 22.7 liter of O2 is produced from 68 gram of H2O2 at STP. 10 liter of O2 at STP is produced from 68 into 10 upon 22.7 gram, which is almost equal to 30 gram of H2O2. Therefore, the strength of H2O2 in 10 volume H2O2 solution is equal to 30 gram per liter or 30% of H2O2 solution. 9.7.3 Structure. Hydrogen peroxide has non-planar structure. The molecular dimensions in the gas phase and solid phase are shown in figure 9.3. 9.7.4 Chemical properties. It acts as an oxidizing as well as reducing agent in both acidic and alkaline media. Simple reactions are described below. Number 1. Oxidizing action in acidic medium. Number 2. Reducing action in acidic medium. Number 3. Oxidizing action in basic medium. Number 4. Reducing action in basic medium. 9.7.5 Storage. H2O2 decomposes slowly on exposure to light. 2H2O2 gives 2H2O plus O2. In the presence of metal surfaces or traces of alkali, the above reaction is catalyzed. It is therefore stored in wax-lined glass or plastic vessels in dark. Urea can be added as stabilizer. It is kept away from dust because dust can induce explosive decomposition of the compound. Please note that till now I have skipped some reactions and some calculations which I suppose should be better dealt by you yourself, because writing the reactions by yourself makes it easy to recollect in your memory, and solving the questions by your own calculation makes it easy and a bit progressive for your preparation. Now getting back, 9.7.6 Uses. Its wide-scale use has led to tremendous increase in industrial production of H2O2. Some of the uses are listed below. Number 1. In daily life, it is used as a hair bleach and as a mild disinfectant. As an antiseptic, it is sold in the market as perhydrol. Number 2. It is used to manufacture chemicals like sodium perborate and percarbonate, which are used in high-quality detergents. Number 3. It is used in the synthesis of hydroquinone, tartaric acid in certain food products and pharmaceuticals, etc. Number 4. It is employed in the industry as a bleaching agent for textiles, paper pulp, leather, oil, fat, etc. Number 5. Nowadays, it is also used in environmental industry. For example, in pollution control treatment of domestic and industrial effluents, oxidation of cyanides, restoration of aerobic conditions to sewage waters, etc. 9.8. Heavy water D2O. It is extensively used as moderator in nuclear reactors and in exchange reactions for study of reaction mechanisms. It can be prepared by exhaustive electrolysis of water or as a byproduct in some fertilizer industries. Its physical properties are given in Table 9.3. It is used for the preparation of other deuterium compounds. For example, CaC2 plus 2D2O gives CaD2 plus CaOD whole twice. 9.9. Dihydrogen as fuel. Combustion. The data on energy released by combustion of fuels like dihydrogen, methane, LPG, etc. are compared in terms of the same amounts in mole, mass and volume, as shown in Table 9.5. From this table, it is clear that on mass basis, dihydrogen can release more energy than petrol. However, pollutants in combustion of dihydrogen will be less than petrol. The only pollutants will be oxides of dinitrogen due to the presence of dinitrogen as impurity. This of course can be minimized by injecting a small amount of water into the cylinder to lower the temperature so that the reaction between dinitrogen and dioxygen may not take place. However, the mass of the containers in which dihydrogen will be kept must be taken into consideration. A cylinder of compressed dihydrogen weighs about 30 times as much as a tank of petrol containing the same amount of energy. Also, dihydrogen gas is converted into a liquid state by cooling to 20 Kelvin. This would require expensive insulated tanks. The tanks of metal alloy like NaNi5, TiTiH2, MgMgH2, etc. are in use for storage of dihydrogen in small quantities. These limitations have prompted researchers to search for alternative techniques to use dihydrogen in an efficient way. In this view, hydrogen economy is an alternative. The basic principle of hydrogen economy is transportation of and storage of energy in the form of liquid or gaseous dihydrogen. The advantage of hydrogen economy is that energy is transmitted in the form of dihydrogen and not as electric power. It is for the first time in the history of India that a pilot project using dihydrogen as a fuel was launched in October 2005 for running automobiles. Initially, 5% dihydrogen has been mixed with CNG for use in four-wheeler vehicles. The percentage of dihydrogen would be gradually increased to reach the optimum level. Nowadays, it is also used in fuel cells for generation of electric power. It is expected that economically viable and safe sources of dihydrogen will be identified in the years to come for its use as a common source of energy. Summary. Hydrogen is the lightest atom with only one electron. Loss of this electron results in elementary particle, the proton. Thus, it is unique in character. It has three isotopes, namely protium, deuterium, and tritium. Among these three, only tritium is radioactive. In spite of its resemblance, both with alkali metals and halogens, it occupies a separate position in the periodic table because of its unique properties. Hydrogen is the most abundant element in the universe. In the free state, it is almost not found in the Earth's atmosphere. However, in combined state, it is the third most abundant element on the Earth's surface. Dihydrogen on industrial scale is prepared by the water-gas shift reaction from petrochemicals, electrolysis of brine. The HS bond dissociation enthalpy of dihydrogen is the highest for a single bond between two atoms of any element. This property is made use in the atomic hydrogen torch, which generates the temperature of 4000 Kelvin and is ideal for welding of high melting metals. Though dihydrogen is rather inactive at room temperature because of very high negative dissociation enthalpy, it combines with almost all the elements under appropriate condition to form hydrides. All the type of hydrides can be classified into three categories: ionic or saline hydrides, covalent or molecular hydrides, and metallic or non-stoichiometric hydrides. Alkali metal hydrides are good reagents for preparing other hydride compounds. Molecular hydrides are of great importance in day-to-day life. Metallic hydrides are useful in ultrapurification of dihydrogen and as dihydrogen storage media. Among the other chemical reactions of dihydrogen, reducing reactions leading to the formation of hydrogen halides, water, ammonia, methanol, vanaspati ghee, etc. are of great importance. In metallurgical processes, it is used to reduce metal oxides. In space programs, it is used as a rocket fuel. In fact, it has promising potential for use as a non-polluting fuel in near future. Water is the most common and abundantly available substance. It is of great chemical and biological significance. The ease with which water is transformed from liquid to solid and to gaseous state allows it to play a vital role in biosphere. The water molecule is highly polar in nature due to its bent structure. Its property leads to water-hydrogen bonding bonds. And here we finish. Thank you for listening to this audiobook.